to the STEP 2023 seminar. Today we have Anton Koробeynikov from Access Softek Toolchains, and I guess he's also part of LLVM Foundation, and he's contributed to Swift and in particular to the compilation pipeline for Swift, if I understand correctly. And so Anton will talk about teaching compilers to differentiate programs. So Anton, the floor is yours.
Okay, thank you, Nikolai, and thank you for hosting me and inviting me for this. Well, so yeah, usually I'm speaking about some other fields, but and different things here and there. But yeah, today I think it would be nice time to talk about some interesting things we can do with compilers, actually. So probably some of you seen all kind of fun stuff happening recently around one of the pioneer in the pioneer company in the artificial learning around all that open AI thing. But so in general, under the label deep learning, artificial neural networks have seen a remarkable renaissance over the last decade. And after series of rapid advances, they now match or even surpass human performance in computer vision, machine learning, machine translation, and gameplay. But if we try to kind of digest the commonality around all these things, then the common to all these breakthroughs is underlying dependency on one particular quite trivial, I would say, algorithm named gradient descent. So essentially, neural network learns by adjusting its parameters in the direction that minimize the observed error on a task. But beyond this commonality, however, the deep learning architectures vary widely. And in fact, many of practical successes are fueled by the increasing sophisticated and diverse network architectures that in many cases depart from the traditional organization into layers of artificial neurons, like written in the textbooks from the previous century. And for this particular reason, recently prominent researchers in the field have essentially called for a paradigm shift from deep learning towards what's called differential programming. Well, essentially programming with first-class gradients based on the expectation that further advances in artificial intelligence will be enabled by the ability to train arbitrarily parameterized computations by gradient descent. But broadly speaking, a neural network is a special kind of parameterized function approximator. And the training process optimizes the parameters W, as on the slide, to improve the approximation of a known ground truth function f based on training data. And while there certainly do exist the myriad of ways to update the parameter of interest, the most popular method is called gradient descent. And I hope that majority of the participants certainly know what it is. So, and the reason for this is largely due to the fact that gradients can be computed efficiently, even for extremely large numbers of parameters. And well, the gradient impacts the direction which increases the loss function the most rapidly, and the gradient descent essentially dictates that the parameter of interest should be updated in the direction of the negative gradient by a small step proportional to some learning rate. So this update step is performed many times, and there are many different flavors of gradient descent algorithms out there. Like in the reality, well, certainly no one sane is using gradient descent in its pure form, like here. Most commonly, you see some variant of stochastic gradient descent flavors that operate in batches of training sample at a time. But for our purposes and for purposes of what's called differential programming, what should happen, or what should we do if both the function and the loss are defined by the program? So how could we do that? So how can we operate in the gradient descent? And I won't talk about numeric methods. So certainly there are numeric methods out there that could approximate the gradient by finite differences and so on. But well, it's usually not the way how the things are operating because, well, of the computational complexity and the round of errors. So, well, there are some existing approaches to differential programming, so it's not something entirely new. And the field itself started to be developed, well, I think back to like 70s of last century. So, but these days, essentially, we might see three generic and different approaches to the differential programming. First is, well, I would call it differential domain-specific language, as implemented in the packages like TensorFlow or PyTorch or differentiation. Well, essentially, that means because it's like small domain-specific language, that means that inside the outer framework or inside the package itself, there would be some new language designed to be differentiated. So, and here is the certainly one inherent problem that it requires rewriting everything using that domain-specific language. And certainly, we are limited to what this domain-specific language provides us. So it should support all operations in the original code. Well, the resulting code and the results usually is quite fast in terms of the computation complexity, as it makes the original code well. But, well, the result might be a little bit cumbersome to write, and well, essentially for us it requires, well, not for us, but for the programmer it requires to write the same code twice. One as the function itself, like on the left, and another one is for like gradient representation, like the code on the right. So we have inherent overhead that we essentially have to write the code twice. Second approach, and I think historically that would be even the like first. It requires for us to be able to overload the mathematical operators. So, and it implemented again in many different packages out there. So it provides the differential versions of existing language constructs. Usually, there is the special types with some side effects. Like sometimes they like record the execution flow and record the operations being done. Well, but still, it may require rewriting to use some non-standard language utilities. In C++ code, it usually requires us to templatize almost everything. Well, sometimes paying quite huge price in the compilation time and in the compiler diagnostics and many other things out there. Well, and as I said, so it's often dynamic. So usually the operations here are having some side effects of recording the operations, recording, computing some elementary gradients on fly, and then interpreting the results, producing the final gradient. And the third approach is source code rewriting. So here we can statically analyze program to produce new graded function in its source language. So well, that approach has its own pros and cons. Well, definitely the package itself should implement parsing and semantics of given language with all bells, whistles, and all peculiarities of the particular source language. It works quite well for legacy languages, like FORTRAN, for example. But even these days, the state of the art in this area cannot support all C++ constructions, for example. So the major disadvantage here is that it essentially requires all the code to be available ahead of time. So meaning that it's hard to use the external libraries, so we need to do some kind of shims or thunks or whatever stuff to represent that boundary where we have to provide the gradients for the external functions. So, all right, so these are essentially three main existing approaches to the differential computing, and all of them has its own pros and cons. But let's step aside from what is already done, and let's step aside what is it, and let's talk about what essentially could be done. So if we check what's going on in that field of deep learning and artificial intelligence, you could see that it does exist the quite usual Python C++ dichotomy. So on one hand, we would like to have the easy-to-use high-level language, like easy to use, easy to write, well, so with faster turnaround time for different experiments here and there. But on the other hand, we would like to have the fast compiled language under the hood. So Python is inherently slow, and usually this is solved by calling all kind of packages that in turn implemented by the help of more performant languages like C++ or whatever. So, and the question is, what if one language could provide both? So, first being easy to use high-level language with many important high-level constructs, and all being fast ahead of time compiled. So, and let me introduce differential shift. So, and recently we contributed quite a lot to that particular feature of the language. So currently it's still in the experimental phase, meaning that it's not the part of the official Swift language standard. But so we still need to go through the so-called language evolution phase. But currently it's available from the toolchains that you could download from Swift.org. So it's already available on the toolchains that you could have on your Mac laptop, should you have one. So the only thing that you need is just to import the module by itself. And as I said, so it could be used with stock Xcode toolchains with some setup. There are some things that might be done if you would like to use that for more embedded devices like iPhones or iPads or whatever. But still, it could be done. And that particular feature, like differential shift, is supported on all Swift platforms. So on macOS, on Linux, and on Windows. And what it does provide. So it does provide this, I would call it first-class automatic differentiation. So meaning that the compiler could automatically generate derivatives for almost arbitrary Swift code. And because it's the part of the language and because it's part of the compiler, so there are broad support for different language features and types, including the control flow. There are lots of the things already supported from inside the compiler. Like we have all kind of type checking that minimize cryptic error messages, and all this essentially boosts developer productivity. And I don't usually like the some kind of pathetic words and so on, but I would definitely say that's more or less unique among the ahead of time compiled system languages. So let's talk about first class. So what does it mean? So the differential programming should be essentially directly integrated into the class for truly first class experience. So what does first class mean? Well, it's becoming more clear to people that differentiation of computable functions, and for us mean that all functions that a metamorpho could write, is not computable. So differentiation cannot be implemented as a library. So we cannot just have, okay, so here is my library that calculates trigonometric functions. Here is my library for the I don't know, for graphics, and here is my library for the differentiation. So no. So differentiation cannot be implemented as a library. So and therefore it could either be a restricted domain specific language or be the fully language integrated as the first class feature.
Anton,
so
possible to ask questions?
Yeah, sure.
So here by differentiation, you don't mean you mean specifically automatic differentiation?
Yeah,
or
right. Yeah, right.
Because numerical methods are still available, but you mentioned this is not what we want to use, right?
Yeah, right. Essentially, because numeric methods could provide you not the gradient itself, right? It could provide you the approximation of its value, and we explicitly separating these two things because we don't want to deal with some imprecisions, with round-off errors, and all these kinds of things. So certainly the approximation could be done as a library, right? So with some additional restrictions, etc., etc. But yeah, but we're talking about the gradients as the computable functions.
Yeah, well, I'd kind of add to that or somewhat contradict, because again, obviously for differentiability, a function should be at least continuous to start with, and we can easily write non-continuous function as a just general function in our programming language. So even numerical methods can do nothing about that. If it's non-continuous, it cannot be differentiated by any means whatsoever.
Yeah, but well, I mean,
yeah, but that's a little bit different thing actually. So certainly we can write the functions with like discontinuous, like well, and usually actually for if we're talking about the applications, we don't need the like complete continuous derivatives. We usually need only directional ones. So and this makes the overall thing a little bit easier from the definition perspective. But well, when we're talking about the definition of like programs or like functions defined as a program, then the underlying thing, and I will talk about this a little bit later, is so certainly it's limited by what we have on the input, right? So and the discontinuities are treated, they could arise in the particular forms in the programs, and I'll also talk about this a little bit later. And we also deal with them also in the some specific way, but I would say predictable one.
Okay. Still, by the way, while we on this page, so the results in the paper say that do they say that even continuous smooth computable functions could have non-computable derivatives or not?
Yeah, essentially like this.
Yeah, that's weird.
And you see that the quite old results. So and all these were discovered quite earlier when the field was developed, like almost half a century ago. All right. So yeah, and yeah, please interrupt me at any time because, well, if someone has questions, because I'm kind of sharing and I don't have right now the second screen, so yeah, in time sharing my entire screen, so I don't see any questions. So please interrupt me at any time.
I will let you know if there are questions in the chat.
Yeah.
I think
yeah,
we can continue. Thank you.
Okay. Yeah. Thanks. Awesome. All right. So as I said, so the differential programming should be directly integrated into the language for like saying in the buzzword terms for truly first-class experience. So, but what does it mean, right? So, well, and is it compiler transformation? So should we just delegate everything to the compiler and let compiler synthesize the gradients for us? Well, not quite. So essentially, differentiation as a compiler transformation is just the implementation detail. So for creating derivative functions, and it's only a small part of creating a differentiable programming language. So and by first class, we essentially mean standard library features like differentiable data structures. And also we need to be able to express functions like differentiable functions in the type system. So, and these are two main things that we need to develop as the language features. All right, so let's start by talking about the data structures. In elementary calculus, only functions are said to be differentiable. So, and as you know, sometimes they're differentiable and sometimes are not. So what types are differentiable? Well, real numbers like here are certainly differentiable. And these are represented by floating point types like float or double. No, I will try to use the Swift syntax here. So certainly because we're talking about Swift. Yeah.
So when you say differentiable type, you mean that a function where an argument is of this type can be differentiated automatically?
Well, it's not only about the functions, but yeah, essentially, like we need to have some, well, we need to figure out like what can be used, right, through the whole differentiation process. So certainly it boils down to the, what could be used as the arguments of functions, what could be used as the types of variables, all these kind of things. Yeah.
Mm-hmm. Thank you.
Yeah. So, yeah, and as I said, so I will use the Swift syntax, but I try to simplify this as much as possible. So, and hopefully the examples are not complex enough and everyone could understand even without knowing Swift syntax and Swift programming language. So, so as I said, real numbers are differentiable. And these are represented by floating point types like float and double. Why the reason why they're structs in Swift is some kind of interesting implementation detail, but for us it's just okay. So it's plain float and plain double, like single precision, double precision floating point numbers. Tensors and SIMD vectors are differentiable when the particular scalar type is, but the integer type is not differentiable. So how we define the common interface for all these types? So how, or in terms of Swift, how do we generalize these types to protocol? Because Swift uses the things called protocols as kind of like language generalization, like templates in C++, for example. All right, and all these types are differentiable because they are real vector spaces. Well, so these types are real vector spaces, and so maybe we can use that. But what about the custom layer type here? And oftentimes,
Anton,
Yep.
So in the previous slide, it mentioned that tensor is vector arithmetic if scalar is numeric. So
Yep.
scalar doesn't have to be vector arithmetic?
Well, numeric here, well, in terms of Swift numeric, means that it's both like float or double, but not integer. So it's like, but so the name is a little bit misleading, I would say. But well, numeric is the common protocol that float and double should implement.
I see.
But not int. So here essentially means that scalar, well, like to be simple here, say, okay, scalar could be like either float or double or something that like, looks like float.
Okay, thank you.
Yeah. All right, so what about the custom layer type here? So, and oftentimes machine learning layers contain properties like configuration variables that are not differentiable, right? So, and types representing vector spaces are differentiable. But since this custom layer contains a Boolean property, so it's not a vector space. So is it differentiable? So how we can extend the language, or what is the notion that we might use in order to introduce some kind of common things for the differentiability? And well, fortunately, we can grab some ideas from differentiable geometry. Well, that can answer this question. And things are not very fancy, so it's essentially just a few ideas, but still. So types in programming languages can be thought of mathematical spaces. And depending on the particular structure of the spaces, we can derive different properties of these types. For us, we should think about the type as a manifold. So, and function f, like with argument type t and with the result of type u, could be drawn here as a function between two different manifolds, manifold t and manifold u. And if we are to do calculus with points on this manifold, or in other words, do calculus with values in types t and u, these manifolds need to be differentiable manifolds. So, and that we know from differential geometry that in such case, they will have an associated vector space called tangent space associated with each point of this manifold. And when we do differentiation at a point, we essentially get a linear approximation at that point between these two tangent spaces. And this linear transformation or approximation is also called a differential or push forward, which is a linear map between these two tangent spaces. And given a tangent vector in tangent space, one can also take point on the manifold and move it along the direction. Move it along the direction specified by the tangent vector. So this operation is called exponential map, and gradient descent uses exactly this operation. So we get in the point, we get in the tangent vector, and we producing the new point on the map. So bringing these ideas and formalism from differential geometry, we can define a protocol in Swift that generalizes all types that we can do calculus on. All right, so let me introduce differential protocol. As mentioned earlier, differential manifold has tangent spaces. So the protocol differentiable defines the associated type called tangent vector that represents vectors in the tangent spaces of a manifold. And the move along method here is the exponential map. which changes the self value, based on the direction represented by a tangent vector. So essentially, in order for type to be differentiable, we need to somehow make it conformable to this particular protocol. So we need to define the associated type called tangent vector. So tangent vector itself should be differentiable, and for that we need to provide the additive arithmetic methods, like being able to essentially call it plus something and multiply by the number. Well, and we need to be able to provide the exponential. So now we can do some kind of simplification. So the Muffalo method, as I said, is exponential map, which changes the self value based on the direction represented by the tangent vector. And here we can provide the default implementation. So in many cases, essentially this, I think this covers maybe 80% of cases when we would be interested in the differentiable types. So so the default implementation is for the cases when the differential manifold is the vector space by itself. So here, the tangent space considers with the type space itself, and then the exponential map is just trivial. So just do just go to the direction and that's it. So with that, standard library types such as floating point numbers and generic SIMD vectors could be made conformable to the differentiable. So and the tangent vector have the same type as themselves. So meaning that, well, as soon as we provide these extensions to the protocol, the compiler could synthesize the default implementation of the exponential map for us. Similarly, in any tensor library, the tensor type itself could also be made differentiable when the generic scalar type is differentiable itself. So again, this extension is quite trivial. So by making the array type conform to differentiable, arrays are now just differentiated itself. So, well, array is differentiable when the element is differentiable, and the tangent vector for array is essentially array of elements tangent vector. So we can think about the array, like the space when the array type is defined is just the direct sum of the spaces of its elements.
Anton,
yeah.
do you understand correctly that discrete types that do not have, like Boolean, for example, they are differentiable, but the tangent vector space there is just the trivial one with like only the zero vector, like it's basically a single one, right?
Not quite, because, well, so for Boolean to be differentiable, we need to define the tangent vector and the differential map, the exponential map. And here we have the problem, right? Because we can, well, given the bool type, you cannot use plus something, right? So meaning that the Boolean type won't conform to the protocol differentiable. So, and the Boolean types are not differentiable. So meaning that if we have something that use Boolean types, we will need to do something with that. Well,
but again, so because the type is discrete, if I understand correctly, the tangent space is just the trivial one where you have it's basically a set with one element, and this element does nothing. So,
well, but you don't have additive arithmetic, right?
Yeah, but so, I mean, the additive thing, it only has to be on the, you have to be able to add something to Boolean, right?
Yep.
But then if this something is just the action that is the identity function, basically, and that's the only thing that you have. So to add something to false, you can only get back to false. You have, I mean, it's the trivial space in this sense.
So for Boolean, yeah, we can
I'm asking because
Yeah.
you had an example where you have a customer layer or something where you have a Boolean as a part of it.
Yep.
So since you have a Boolean as a part, you have basically a product of two spaces, one that you know is differentiable, and the other one is Boolean, right?
So, so here is the thing. So while with Booleans, we can like kind of make some reasoning about like what we could do that. So we cannot easily extend this for the like proper integer types, like when we have like more than two things and so on. So
right.
and well, so you're correct that we essentially have like, so we are essentially having the product of like two spaces.
Maybe I can phrase it differently. For integer and Boolean, we sort of know that they do not have any interesting differentiable property, but there's the trivial one. So when we compose them with other things, we only need to know how to differentiate the other parameters, and we know that Boolean and integer have to stay the same. They cannot change.
Right. So essentially, so that's that I wanted to say that you're right that for like that custom layer example, we have like product of two spaces and so on. But the thing is, and this is how in that particular case the thing should be viewed. So you can differentiate through the Boolean, but in the cases when you have to calculate the gradient, like for the gradient descent, you essentially have that particular like, parameter as fixed. So meaning that, okay, we have products of two spaces, but in any particular time, we are operating one part, right? So either when the parameter is true or false, but we are not able to like flip between these two parts.
Yes. Yeah. So I understand that in the implementation, you obviously want to ignore the Boolean and just to differentiate only on the parts that are smooth and ignore the discrete parts. What I was asking is that in mathematics, technically Boolean is differentiable. It's just that the tangent space is not very interesting, so we can ignore it in the implementation.
Right. And the way how we ignore that is that we don't make the Boolean type to be conformable to that particular protocol. So, because
when you how do you make custom layer differentiable? Do you I believe you have some deriving mechanisms, right?
Yeah. Let's wait about like 2 or 3 slides more, and I'll just show you. So yeah. All right. So here we have arrays, and arrays could be certainly made differentiable as soon as the elements are differentiable by itself. So we have same things for dictionaries. So again, we can view the dictionary just the collection of things, and well, all right. So we can make them differentiable if the values are differentiable. And in Swift standard library, there is also the optional type. And we can also make the differential by declaring a simple conformance. So here we have the rapid type, and okay, so the optional is differentiable as soon as the rapid type is the differential by itself. So now let's get back to that custom layer example, right? So let us make it conform to the differentiable protocol here. So we need to define the tangent vector, and we need to define the exponential map here. So, and essentially, since we ignore the I would not say ignore, but since we know that every time we we would use that particular thing for the derivatives, the use bias Boolean value will be fixed, right? So meaning that so for us, the tangent vector would essentially contain only the differential parts here, And the exponential map is again well, just like move along the direction of like both fields here. So in tangent vector type contains properties that conform to differentiable. So meaning that we should not bother about all these things. So, and the good thing is by default, the compiler could synthesize this for you. So meaning that if you have the non-differential fields, then by default, we just ignore them in that particular things. And even this, it would allow us to, for compiler to generate that exponential map by default for us. So here is it. Hopefully that answers to your question. So long story short, so for like integers or Boolean properties, our reasoning or our thinking about this, it should be when we do some kind of like gradient calculations, these fields will be just kept fixed, and this is how we define the tangent vectors for everything else.
Anton, is it possible to differentiate recursive types?
Yep. So certainly
I'm sorry. Can we go back?
Yep.
To the previous slide. I believe in the move function we should replace x with weight and y with bias.
Oh yeah, right. So definitely.
Direction.
Sorry. Yeah.
Right. Thanks.
Yeah. Sorry. Right. So it was typo. I renamed the fields here, but not in the move. Yep. All right. So in the data structures could be fully polymorphic here, right? So we can have the generic types, and as soon as the generic type conform to the particular thing, we can proceed there. So
I'm sorry, I think there was a issue again, because point is parameterized only by t, which is supposed to be real, and u isn't constrained.
Right, and it's it's perfectly okay, because again, depending if you conforms to differentiable like protocol or not, the compiler could synthesize different tangent vectors for you.
What is I think the question is, what is type U?
Well, so here it's not defined, right? But well, it could be either some like defined type, or it could be like generic type if you put into the points like definition.
Okay.
All right, thanks.
Yeah. So, and at the heart of differential programming language is the ability to express differential functions. So, we represent differential functions as first-class values in Swift. So, and in order to do this, we need to extend the type system a little bit. So, as I said, so Swift supports first-class functions. So we could write high-order functions like map here, but we want to represent differentiable functions. So that means that there should be some kind of extra information that allows the function to be differentiated. So the question is how do we represent this extra information in the function type? So can we add some kind of special function type or whatever? And the thing is that yes, because the special function type in Swift already exist. So, and therefore we can look at some prior art from language interoperability. Well, so the thing is Swift is natively interoperable with C and Objective-C, and well, these days even with C++, but still C++ thing is kind of work in progress. So, and C functions are imported into Swift as a special C function type with different restrictions here and there. And same for Objective-C. So, well, but why we should bother about some special types here? Well, the answer is because functions in different languages have different common conventions. So, and well, so certainly this is the implementation detail, how function calls are implemented in a language, but well, this detail is complex enough and important enough that we have to expose that as the language feature. So let's see a little bit more close example. Let's declare the add1 function in C, right? So, and I can refer to this function as the function pointer by defining the global C variable, right, in C. And when I import this C file in Swift, the function pointer is imported as the global variable with the additional convention C function type. So, and I can explicitly cast the convention C function value to a regular Swift function. So, well, the casting is actually implicit, and I can call the Swift native high order map function, which takes normal Swift closure. And the C function pointer here will get seamlessly converted into a Swift closure. So don't have any problems here. Well, but still, why this type difference needed? So why we should just don't bother about it. So, and can we just drop that convention C thing? Well, so earlier I mentioned the calling convention, but actually there is another important reason, which is the function runtime representation or application binary interface. So in C, functions cannot capture values. So, and therefore C functions are represented as the single function pointer in Swift. But in Swift, Swift functions can capture values, and therefore Swift functions are essentially represented as a bundle of two things. So they're like fat pointers, a function pointer and a context pointer to capture values here. And converting a convention C function to a Swift function, like native function, is just adding a null context pointer. So, and we can say that particular like convention C functions, or that calling convention is a subtype of native C functions. Like here. All right. So, and having this notion in mind, so having this thing that is already implemented in the language. So let's try to design or discuss what might be done for the differential function. So
I'm sorry.
Yeah.
Can I just clarify? I'm always
Sure.
confused with the subtyping relation and whether it points into the correct direction. So if we have a C function, we can always use it as a Swift function, right?
Yep. Yep.
So whenever we expect a Swift function,
pass
So C function or Swift function. So it's the other way around, probably.
Yeah, you're right. So somehow the arrow got flipped. So certainly the convention C is a subtype of native Swift functions. You're right.
Mm-hmm. Thank you.
Yeah. Sorry. All right. So and just like convention C functions, differential functions are subtype of normal functions and can be differentiated. So, and this is how the differential functions are represented. So, yeah, things got flipped here as well. So, sorry. So, the arrow. So, in differential functions store extra function pointers to derivative function. So, they're even more fast. So, a differential function.
Again, just to clarify, because I think this is not very obvious. With the differentiable slide, we can always turn a differentiable function into regular one by forgetting the derivative, right?
Yes.
And we not just have.
Yes, but and this is what the next slide is for like upcasting and downcasting. So what happens about the conversions? So well, yeah. So as Ildi said, for upcasting a differential function to normal function is free, right? So we just like drop the derivative, like pointer, and that's it. So but downcasting, on the other hand, depends on the function's structure. So the function at 1 here, defined here, is differentiable, so it can be converted to a differentiable function. So in general, downcasting a normal function to a differential function triggers differentiation by the compiler. So, so what are the requirements for a function to be differentiable? So, there are two cases. First is then one marks the function as differentiable. So here, the compiler verifies that the function is differential itself. So in second case is a little bit more elaborated. So second case is that the function is not marked with anything, but the function is composed of functions that are differentiable. So, well, but since the function is not marked with the differentiable, when does differentiation process, like, so when it actually happened? So it happened at the point when the function is converted to the differentiable functions, and this happens implicitly whenever you use the API, the application interface that takes the explicit differentiable function argument. But we'll talk about this a little bit later. But let's.
I'm sorry.
Yep.
May I clarify?
Sure.
I don't quite get. Yeah, when we explicitly say that particular function is differentiable, do we provide this explicit derivative as an argument, or how does that happen?
We may do this, but well, so the thing is, certainly when we in the second case where the compiler should be able to verify that each function call happening here.
Yeah. Second case, I understand. Yeah, I'm asking about the first one.
Right, but how it can do that? So the compiler, that means that the derivative should be either provided somewhere, right, or the compiler should trust that the derivative does exist. And so if there is no function body, like just the declaration, right, so the compiler should just trust the programmer that the derivative will be somehow provided, right? So and this is the first case is kind of one of the possible cases when we can forward declare, okay, so we will provide the derivative somehow. That's it. So optionally, we can explicitly provide it, say, okay, the derivative for that particular function is implemented here. But yeah, the first thing is essentially promise that it will be somewhere. And that means that, okay, and by this attribute, the compiler should say, okay, so there will be the derivative provided somewhere. So there are the particular name inventing rules. So meaning that the compiler should know what will be the symbol name for the derivative and use it in the whenever that scene function, if it will be called somewhere, then the compiler would know how to call the derivative itself.
Yeah, I see. Thanks.
Yeah. So things a little bit interconnected here. So and I'm trying to untangle it from different points of view. So yeah, there are some interdependencies. As I said, so we'll talk about the programmer interface for derivatives a little bit later. But let's go through some school level math and let's talk about the function differentiation process. So I'll just took some small example. So we have more or less trivial function and just normal quadratic laws with some additional regularization. So if we would try to do the school level gradient, school level partial derivative calculation, we will just need to remember all that rules, chain rules, and essentially see that it's composition of different functions. So we need to calculate the like derivatives of complex functions using the chain rule here and there. So, and you could already see that this process is a little bit, well, I wouldn't say like cumbersome, but a little bit complex. But you could already see that there are some common sub-expressions that could be like used to simplify the whole things. But here you could see that in terms of the computational complexity, we would need to calculate the partial derivatives for each parameter separately. And well, that means that the computational complexity for this particular school site approach is proportional to the number of the parameters multiplied by some kind of like complexity of the input functions. But actually, and I think this was one of the breakthrough in the automatic differentiation, is that we can do the differentiation from different sides, let's call it this way. I would not boil down into the like more mathematical details, but well, so from the mathematical standpoint, our program is just the composition of many functions, right? And we all know that in order to compute the gradient of the composition of functions, we need to use the chain rule. So, but the chain rule actually is fully associative, and therefore, well, so. And unlike the symbolic differentiation that operates on math expressions, automatic differentiation operates in the code. So, and the chain rule is used to define temporary values in a program. And well, so and there are two common styles of automatic differentiation in the traditional sense. So well, actually there are more, but the whole spectrum of the things. But the so-called forward mode automatic differentiation starts with the partial derivatives at inputs, and then they end by computing partial derivatives at outputs. While reverse mode automatic differentiation starts with partial derivatives at outputs and ends by computing partial derivatives at inputs. So like mathematically, forward mode corresponds to the fully right association of the chain rule. So in reverse mode corresponds to fully left associations. So in, well, different here, like different associations of the chain rule produce the same result, but they may differ in the computational complexity. Well, one could essentially think that, well, so we need to compute, if we are to compute the complete Jacobian matrix, right? So it is composed by the multiplication of the Jacobian matrices of like each functions that we are composing, right? And essentially we have the huge matrix composition. And depending on how we put the brackets in this like composition of matrices, like if we compute them from left to right or right to left, we may end with different computational complexity. So, but it turns out that in the cases that are important for optimizations or for like deep learning and so on, usually the functions have the very particular shape. So we have bunch of parameters, bunch of arguments, but only single result, meaning that the functions all be like loss function, right? So we just have single result. So therefore, the reverse mode of automatic differentiation, usually it's much more cheaper than the forward mode. So let's return to our example. So if I would, like,
while before we get into the weeds, I have for now kind of more high-level question.
Yep.
Yeah, on that side of reducing the computational complexity. When we do reverse mode differentiation, do people intermix? Have they looked at intermixing these stages of differentiation with compiler optimizations, like usual stuff, that code elimination,
Yes.
Common sub-expression extraction or stuff like that, to reduce complexity even further? Is it kind of a common thing, or does it make sense?
Yes. Yeah, that's pretty common thing. So certainly, so here are both pros and cons of doing the AD on the optimized program. So, on one hand, essentially, because because we are inside compiler, so depending on the stage when the automatic differentiation happens, it can only operate on the optimized code, and so certainly we can optimize the generated derivatives further in the compilation pipeline. So yeah. So in here we need to seek the balance, because computing derivatives on the already optimized code might be more complex thing from the compiler perspective for some reasons, but this might end with more optimal code in the end. So if we move the AD closer to front end, so deriving the derivatives on the non-optimized code is easier from the compiler perspective, but the resulting code might be more harder to optimize. So we need to strive, we need to seek the balance. So, and it's a little bit tricky thing, but certainly, yeah. All right, so let me try to very quickly, within one slide, try to explain what is reverse mode automatic differentiation. So for those who are not familiar with that particular thing. So essentially here we consequently treating the final loss function, the LREC, as a function of different arguments, like L, R, and so on, evaluating derivatives executing the program essentially in reverse, like here. And all right, so certainly there is no magic under the hood here. Compiler is not a miracle, and it cannot provide you derivatives for particular for any arbitrary function, right? So meaning that someone should provide the derivatives for the common textbook functions somehow. So, and this is how we can define custom derivatives. So let's start with a simple example. When you import the foundation in Swift, you import the function called sqrt, which calculates square root. So it's defined elsewhere, so we don't see its body, we don't see its implementation, and therefore it's not differential by default. So because compiler doesn't see its body, and therefore it cannot deduce if the function is differentiable or not. So, and therefore, if you try to differentiate it, you get the compiler error. But how can we make it differentiable? So we can just make it differentiable by defining derivative for it. So, and let's start defining the custom derivative for the square root. The derivative takes the arguments of the original functions and returns a tuple. So the first element is the result of the original function, and the second element is the linear map representing a transpose of linear approximation of original function for the given argument. Because we're doing the reverse mode ID, so this transpose of linear approximation is called a vector equivalent product functions, or VGP functions. So by marking the derivative function with the derivative attribute, we tell the compiler, whenever you differentiate square root, use these derivative functions. And retroactively defining derivatives for the important functions is, it's really a great thing, because it's not like we need to annotate the whole standard library in order to start. No. So we can add the derivatives to functions as necessary when we try to move forward through our code. So so now all libraries that import our library will see the square root as the differential functions, and this is how we make the function to be differentiable. So
I have a question about the derivative of a square root. I think maybe this is unrelated, but I think there's some Quake magic computation of the inverse of a square root of x using some bit magic. Is that used in any way in the actual library for differentiable Swift?
Well, by default, no. So, because like here we defining the the derivative for the library functions, right? So, and here is for us, and I kind of like sweep some details under the carpet. So, and I was talking about like the exponential maps or push forwards, but essentially because we are like mostly interested in the reverse mode ID, we need to have pullbacks, the transposes or a joint of pushback. So, but yeah, here we provide the derivative, right? So here is the because transpose, so it takes the output, and we need to get the input of the derivative. So, and it's how the division and multiplication is implemented for the derivative itself, right? So, so essentially the compiler relies on the particular implementation, right? So if one would provide the library of optimized gradients, right? So it certainly will be used.
I see. Okay.
Yeah.
Thank you.
All right. So let's
just saying that I'm not sure how much more material do you have, how much more in the presentation.
Yeah. Well, so I think we are maybe around like so 1/4 of what we have in so far.
So there is about 15 minutes more.
Yeah, something like that, I think.
Okay, I think we can do that and then have questions after.
Okay, all right. So let's talk about the operator. So the main core operator here is value with pullback. So it takes the value and differential functions and returns the original result of function. And the pullback, so they said this transpose or joint or differential, which computes the directional derivatives. And everything else is essentially implemented in terms of it. For example, the value with gradient functions, it works for scalar output functions and evaluates the pullback at 1. And gradient also returns in the gradient values and discards the original results. So, and there are many more things here that we can use. Like here is the example how we can use the differential operator. So if you have the function that we're going to differentiate, then we just call the value with gradient and get the tuple out. So, and here is a simple example, right? So how we can use that. And here is even more. But essentially here is a simple example implementation of gradient descent in differential Swift. So we just call the value with pullback and go into the direction of the exponential map, and we are done. So pretty trivial, but it works. So now let's talk about the compiler. Swift compiler takes the Swift source files and compiles them to the native binary. The more detailed pipeline is here. Like first, Swift source code is parsed into the AST, the abstract syntax tree. The AST then goes through the type checking, and then it's lowered to the Swift intermediate language called SIL. Then mandatory and optimization process are run, and finally SIL is lowered to LLVM IR. All right. Well, and what we have here is that the automatic differentiation transform is in the compiler is just another mandatory SIL pass. So meaning that it operates on the intermediate representation inside the compiler. So and it runs as the part of the standard compilation pipeline. So here is example of a simplified cell. Like it's kind of the static single assignment intermediate representation. So I clean the seal for the clarity on the right, so it's not the the real seal, but yeah. So and yeah, here essentially the seal for the function that calculates the the result of multiplication of sine and cosine. Yep.
Can I ask if in this Swift intermediate representation, if we have functions as closures already, or if we have them still as Swift functions?
Well, so the answer is a little bit more elaborated. So it depends. Like the context itself is sometimes implicit, sometimes explicit, depending on if the values escape the particular function through the while being closure of. So, but
the closure conversion, the overall closure conversion happens later.
No. So in seal, it's already explicit.
Okay. Okay. Thank you.
Yeah. Yeah. So here we already So if I understand correctly what you wanted to ask, no. Here we explicitly see all the values that are closed upon. So and we know what's going on and so on. So seal is it's much lower level than the Swift itself, but it's but still it contains lots of high-level constructs that we could use. All right, so differentiate in compiler has 3 parts. So first, we analyze what needs to be differentiated. Second, we diagnose the operations that cannot be differentiated. And finally, the differential transform produces derivative functions. Activity analysis is the static analysis that detects what exactly needs to be differentiated. So in here, we have 3 different notions for values. Varied values depends on the input. Useful values contribute to the output. And active values are both varied and useful, and they need a derivative. So first, we do analysis in the forward direction. So for the varied values, every value that depends on the input is varied, like here. Then we do analysis in the backward direction. So in every value that contributes to the output is a useful value. Put these 2 analyses side by side. We can take the intersection of varied values and useful values. So in values that are both varied and useful are active values. So when differentiating a function body, we differentiate every intermediate function that has at least 1 active argument and 1 active result. But actually, there are more. So not only do active values tell us what function one has to differentiate, it also tells us what function parameters to differentiate with respect to. In this particular example, we know that we don't need to differentiate multiplication with respect to the first argument because it's not active. And now we know what to differentiate, right? So these things are inactive, so therefore they could be skipped. As I said, differentiation is implemented as the seal function transformation. So again, there are 2 steps here, and each of them generates new kind of derivative function for the given function. So the first step is the VGP generation. So it's vector Jacobian products. So VGP function takes the same arguments as the original function and returns a tuple of the original result and the pullback function. So the transpose of the push forward. And second step is a pullback generation. Here we're essentially executing the captured pullbacks from nested VGP calls in the backward manner, doing the reverse node AD. And the joins of individual instructions are automatically emitted by compiler.
But previous example, so you mentioned that not everything should be, if you go back one slide. So
like here. Oh, sorry. Yep.
Oh, not maybe to this slide. Yeah. So here you say that cosine can be not computed into the derivative and the first argument of multiplication, but that in the code when you showed us VGP that is generated, it seems that it doesn't do that. It doesn't.
Because it depends on because it's different code. You see the cosine and sine both depends on the input argument.
It's different code. Okay, I didn't notice. Okay. Okay.
Yeah.
Thank you.
Yes. So here we need to differentiate like both sine and cosine, right? So, all right. So let's return to the very first question. So what to do with discontinuities? So control flow gives us functions that the ability to represent the conditional operations. So it's certainly mathematically, control flow makes it possible to express discontinuity via piecewise definition of functions. So the compiler can naturally differentiate through control flow structures and produce piecewise defined derivative functions. So this is how we how the compiler assumes that the compiler assumes that the user knows what they're doing, right? And if the function is defined piecewisely, right? So certainly there might be a discontinuity at the point of condition, but the derivative produced is, again, piecewise defined derivative here. So, and the key to differentiate function with control flow is to track the original execution path through the function, because, we need to know which branch was taken. So certainly there is certain overhead here. Situation with loops is slightly more elaborated because when the loop trip count is not known, so we need to have some kind of dynamical allocated storage for values produced. And the trick key is how to do that efficiently. Clear diagnostics are essential for productivity. Like differential programming in Swift, provides all kinds of different compiler diagnostics to ensure that things are operating properly. Like here, so it's not like you will see such kind of error these days because the whole standard library is already annotated with derivatives. But another thing is Swift libraries are distributed as modules, which provide an API interface in a opaque binary format for client code to use. And after importing the library, we can compute derivatives of functions that have registered derivatives. Like here, if we import syn from libc and try to differentiate, the compiler will produce the error message, and also functions that convert values to non-differential types and convert them back are not differentiable. So in compiler can detect these cases and provide compile time error messages. All right, let me use the remaining 2 minutes for some examples. So I try to just the gradient descent itself is a little bit boring, but let me show some results that were, I think they announced pretty recently, maybe a week ago or so. So these days, one possible application for the differentiable computing is the ability to build proper digital twin models. And my example is from a passive logic company. And they provide digital twin models for buildings. And the motivation is that buildings contribute a lot to the global energy consumption. It turns out that very few buildings are automated. And if we try to build the proper digital twin model for the building with proper physics, with proper all things like that, then we can make automation possible because we can try to optimize for different parameters here. So in the first question that is answered, so why not traditional deep learning here? So why we cannot just have the data set with some things how we can cool or heat the building and then build some predictions? And the answer is that every building is unique, and therefore we cannot build no one model that fits all. And another problem is that training data generation is pretty slow because usually, we need to gather the data from like history, from the whole like annual cycle. And that means that if we are to learn on like 1,000 data sets, that means that we either need to wait for 1,000 years or we need to like look into like many different buildings. And this doesn't scale well. And essentially, the implementation currently is implemented in differential shift. So with like proper physics models and proper like for the like material for falls, for the places where the like AC are located, etc., etc. So and why they need the differential shift? So they can do similar things in like TensorFlow or PyTorch. But it turns out that for that particular task, like things are quite slow. So like for the derivative computation, like for example, the code like on the slide, the differential shift is several orders of magnitude faster than TensorFlow or PyTorch. So meaning that you could optimize the systems with like thousands of parameters here and there, including the complicated and sophisticated physics model with the like heat transfer and the like airflow, etc., etc. All right, so I think my time is run out, and I would open to any questions.
Thank you, Anton, very much. Let's thank the speaker. I don't know, maybe silently. And yes, any questions?
Can we consider this approach as metaprogramming?
Not quite. So because it's not the kind of metaprogramming as we think about like C++ with templates or some other things. So no. So that's essentially the way how we extend the language with some non-trivial constructs. Right? So these days compilers could like do like all kind of like optimizations and instrumentation, etc., or like adding security to the automatically. This example is, I would say, to my opinion, is much more liberated because it provides how we can extend the language itself, like the type system, and the like design the completely compiler guided feature on top of that.
Any more questions?
Я думаю,
I had a question.
чате вопрос.
Yeah, there's a question in chat by Alexander. You can probably ask yourself.
Yeah, sure. So I'm particularly interested because of in a previous experience. How do you handle mutations, destructive updates in the automatic differentiation pass?
Well, so the mutation essentially derives a new value, right? So meaning that we need to track where the loads and stores are happening, right? And well, so when the code is in the particular intermediate form, we just essentially track the value before mutation and value after mutation, and we need to deal with both values.
Right. And in particular, follow-up, how does that work for arrays? Because, arrays are a bit more tricky. I mean, mutating updates, arrays,
Yeah, right. So you're correct. So the things are a little bit tricky for the things like arrays or dictionaries. So like things that are not, let's call it value types, right? So, and the tricky part here is to ensure that we are not creating the whole copy of the complete array. So there are some tricks like implemented in order to reduce the performance overheads in that particular cases. But well, it's doable, but well, little bit elaborated and non-trivial. So essentially, for arrays, we are not looking into the like what I have shown was a little bit oversimplification. In the reality, we have the kind of differential view over the array. So we don't look into the whole array, but try to only deal with the subset of values that are participating in the expressions, something like that. So certainly, if all values are touched and updated, well, we have to deal with like all the values in the array, right? But in many cases, either all the values are just read and it's fine, so we don't bother about it, or only few values are updated.
Anton, another question in the chat by Sergey is that so you mentioned that it's possible to overload operators in C++ to get differentiation, automatic differentiation. You mentioned, I think, that it computes the derivative dynamically. But still, the question is. Have you compared the performance, the speed of the C++ implementation versus Swift versus PyTorch, etc.?
Well, so it's not possible to do the complete apples to apples comparison here, right? Because first of all, in order to do the operator overloading thing in C++, you essentially have to rewrite your source code to be compatible with that approach. And sometimes these approaches are very I would say, hacky. You just go like define double A double or define double I double somewhere like globally, right? And then let the magic thing to work. Like, let's think about like external libraries and what will happen if we will be not careful enough. That's the first thing. And and again, the comparison is not very it's not very honest, because in Swift Swift is, I would say, a little bit more high level with C++, with lots of the with some additional overhead that we have paid for the increasing level of abstractions and so on. So, but what we normally do use is that we compare the what is the overhead that is added for the AD. And I would say that these days in Swift it's fine. So I mean that the gradient calculate the present optimization process could eliminate the overhead quite nicely, and the performance of the generated gradients are comparable, proportional to the running time of the original function. So this is what we are actively contributing these days. So trying to ensure that all the overheads are removed, and so on. But so in many cases, answering the original question. So in many cases, the performance could be similar, but again, it's hard to compare apples to apples, because we're all talking about, okay, because if we are to rewrite or do the second copy of our program with the gradients on top of that, that's additional overhead for writing, for maintaining, for updating, and etc. But if you pay that, so certainly we can easily get the very, very high performance code. But so it's all about pros and cons and what we should pay for.
Thank you. If I remember correctly, in differentiable Swift, it is possible to differentiate higher order functions, so functions that depend on other that take other functions as arguments. So can you maybe give an example of such a function, maybe a simple one that would make sense? Why would anyone want to do that even?
Well, so it's not like let's take from the other side actually. So, well, it's possible because we do support the differentiable generics, right? So it's not like we like hardcode like floats or reals or whatever, right? So because like essentially the compiler transforms generic enough. So as soon as the type conforms to the differentiable protocol, we can differentiate that particular type or through that particular function, right? So it means that if you have the higher order function, right, and you like, which is like generic thing, and if you can like somehow like conform its arguments to like differentiable protocol, then yeah, things will just happen automatically.
Mm-hmm.
So I would not say that it does make sense in many cases to different higher order functions, right? So like, what is the derivative in the direction of the function, for example, right? But well, so it just like happens in the generic way. Let me answer this way.
Mm-hmm. Okay, I think Alexander also mentions in the chat that when we do Bayesian inference via variational inference, then differentiation with respect to functions
Yes.
is useful. But unfortunately, I have exactly zero knowledge about this.
Well, yeah, right. So
but I think this is useful for others.
Right. So I was talking about the gradient descent because it's much easier to explain for the wider audience. But certainly the ability to compute gradients of the arbitrary functions could be made useful like in many different cases. Like for Bayesian inference, yes. We can think about Hamiltonian Monte Carlo when we can like speed up the like Monte Carlo process if the function itself is smooth enough, right? Mm-hmm. So there are many different areas when the automatic differentiation could provide lots of interesting cases. And actually, some packages like stand for the Hamiltonian Monte Carlo already have some kind of AD library under the hood, like tuned to the particular like usage in the particular package, right? So that's quite. That was quite interesting observation for me, like when we started to do that. So it's not something AD like automatic differentiation. It's not something we talk every day, like, but it's surprisingly widespread in some areas. It's just treated as the implementation detail. So and yeah, here we're just talking about okay how we can make it like generic enough to be universally usable here and there. So one could think about the like certainly about like application in the financial mathematics, like for example, like if we talk about the option pricing, right? So usually the models are formulated in as a solution for the particular stochastic like differential equations, and we need to be able to like compute gradients of solutions for these equations. And if the option model is sophisticated enough, so it's not like simple, I don't know, model that could be solved with like Black-Scholes equations or some kind of similar thing. Yeah, so it could be defined programmatically. Then we can integrate the differential equations like numerically. But then we can automatically differentiate the numerical integrator, providing some kind of like approximation of the gradients, but at least not to pay price twice because we like approximate due to the solution and for the derivative itself.
Right. Thanks. Thank you. Do we have any more questions? Maybe I will have one last question. Since you are participating in a compiler project and you are basically implementing a compiler or a part of a compiler, I have a question. Is there a use case for differentiable programming when you are developing a compiler?
I don't know. Well, so the one particular thing that comes to my mind. So in many cases, there might be some heuristics that particular optimizations are driven, right? So like various thresholds or like parameters here and there. And sometimes, like not sometimes, like in the majority of these cases, the values of the parameters of these heuristics are selected by common knowledge or by some like observation, etc., etc. So we can think about, okay, if we can provide, like, if we try to optimize for them, then probably computing gradients could help to speed up the things. And actually, there are some current research in this area, frankly speaking. Like, for example, people are building like models for the inlining cost decisions. People are building models for the register locator spilling like places and spots. Yeah, for the tuning of optimization pipeline. So why not?
I see. Thanks a lot. If we do not have any more questions, then I would suggest we thank the speaker again. And Anton, thank you very much. It was a very nice talk. I certainly learned a lot. I hope others did as well. I will now stop the recording.